Hey guys, hope you're all doing good and welcome to a new video. In the last video, we submitted the channel flow simulation in parallel using 4 processors, and I just wanted to say that the simulation ran through. So this also gives me an opportunity to explain like some of the real cool features of Sigwin. So you can see that the last command that I typed is tail log file. So what is log file? Well, that's the name of the file in which I'm sending all the outputs. Tail of a file basically means its end. So when I type in tail log file, I can basically just look at the last few lines, right? I think by default 10 lines are printed. So if I type in tail -20 space log file, it's going to give me the last 20 lines. Now you can see that in total the simulation took 122 seconds, and it took 27 seconds to solve transport equations and 81 seconds to actually write the output files. So what does output files mean? So if I type in ls, you can see that there are so many files here. It might be easier to basically look at this from the graphical user interface. So here you can see that there are so many .out files, and if I basically sort them by the type, you can see that you have dat files, which are the input files, echo files, which are basically the copy of your input files. So this used to be a great feature when people were trying to edit these input files manually. So sometimes you would make an editing mistake, right? So for example, you would change the .in file and you would run the simulation, but you might have made a mistake. So the .echo files basically keep or make a copy of your input files just after the simulation was submitted. So that way, say that someone else comes in and changes the input file, right? You can still go back to your .echo file to make sure what was the input with which you ran the simulation. All right, hope that makes sense. And then you have a lot of .out files. So these are your ASCII files. These are readable files. So for example, you can see that there's a file called mass average flow.out. I can just open this guy, and this basically contains for each and every cycle what is the mass flow rate through boundary ID 1, which is your inlet boundary. What is the total pressure there? What's the static pressure there? Basically the averaged quantities, and there are so many columns of useful information, right? And I can close this guy, and you can see that there are so many .out files. Then you have your restart files. Your restart files are basically your checkpoint files, right? So let me just try opening a restart file, right? You will notice that first of all, it's not at all readable except for the first line. The first couple of lines give us a lot of useful information. So this right here tells us the cycle at which this restart file was written, which is 13,000, right? So this is really useful for me. And you can basically see that there are 3 restart files in total. So if I open this guy, you can see that this is written at 15,000, which is the last cycle. Now what else do we have? Apart from all of this, we have a folder called output, and here you can see that there are so many files. These are what you call as your 3D post files. So let me just open one of them. This is also a binary file, meaning you cannot read it. It doesn't make sense. Don't try to edit this file. If you edit something, you are going to corrupt it. So let me just close this guy. So what we need to do is we need to take these output files and we need to convert it into a form so that we can post process it. So that is why we are going to go back to this Google Drive folder, and we are going to download this post-convert.exe file. Right, so I'm just going to take this guy and I'm just going to download this. So what does post-convert do? Well, it takes CONVERGE 3D output files and converts it to a form so that our post-processing program can understand it. So what is our post-processing program in this case? Well, that is ParaView. Now I've already downloaded ParaView, so because it's a large file, I don't want to download this again, right? And you can see that I've also unzipped it. Right, in the Google Drive you will see that there is a zip file. What I've done is I've just unzipped it, and if I open this, there's a folder called bin, and inside that you have paraview.exe. So this is the program. So what you can do is you can just try to launch this guy, and just make sure that it opens up. Yeah, so make sure that there are no errors. Now here again, if you have 2 graphics cards, especially an Intel based one and Nvidia based one, try to launch ParaView so that you're basically using the Nvidia graphics card, not the default graphics card. So for now, what I can do is I can close this guy, right? And what I'm going to do is I'm going to copy this post-convert file, and I want this post-convert to be available in any location, right? Because I'm going to be running a lot of simulations in this course. Each and every time I don't want to copy this file. So what can I do? I can go to C:, program files, I can go to converge, and I can paste it right here. If I paste it here, it's going to be visible from everywhere else, correct? So let's open this guy. Let's close Sigwin and relaunch Sigwin and type in POST, and immediately you can see that post convert is available. Alright, so let me increase the font size a little bit and go to CD converge runs, CD support cases, CD channel test 2, channel test _2 I believe, and then we're going to go inside the output folder, and here I'm going to type in post convert.exe, right? So this is launching the converter program. And for some reason there is actually no output. Upon some research I found that this is actually because of Sigwin, and it has to apparently be updated in order for this to work. And to kind of prove that this process actually works, I'm going to use the traditional command prompt, and I'm going to navigate to E drive, go to converge runs, and we are going to go inside support cases, and we are going to go inside channel test 2, and we're going to go inside output. So here if I type in post convert, you see that I'm immediately getting a menu like option that is not coming in Sigwin. So that's the problem. So for now let's use command prompt to demonstrate this. So I'm going to type in a case name which I can call test, and I'm going to hit enter. It's asking me in which format I would like to do the conversion. So I'm going to go with ParaView, and I'm going to go with option number 10. And boundary surface output, I would like to do that, and I press 1. And which are the files? Well, I would like to convert all the files. And which are the cell variables? I would like to convert all the cell variables. And you can see that it's converting all the post files into a form that ParaView can read. Now might be a good time for us to actually go inside the bin folder of ParaView and launch it. And you can see that this process took only 10 seconds, but that's because the simulation is really small. If you're running an IC engine simulation, then this process can take several hours. So let's close this guy. Let's click on open, and we're going to go to E:, and we're going to go inside converge runs, support, and then channel test 2 output, and you're looking for this test _.vtm file. So this is a group file. So if I just expand this, you can see that it contains all the VTM files. So I'm just going to select all of them together, and ParaView gives me a nice interface. I don't have to select everything. I can just use this option, and if I click on OK and click apply, all the files are going to be loaded. So this is my geometry, right? You can see that it's 2D, right? And what I can do is I can first create a slice to basically cut this, and I don't want to cut it like this. So I want to cut it in such a way that the normal for the cut plane is along the Z direction. And if I click apply, the cut is going to be shown. I'm going to hide this option so that the plane is no longer visible. And I'm going to uncheck triangulate slice and click apply. And instead of surface, I'm going to go surface with edges, and that's going to show the computational mesh. You can see that I have roughly 10 cells across the gap. Right, so this is kind of matching with what I expected, and then we are going to look at this plane along the Z direction. So this is basically a simulation. So what I can do is I can color this by, say, velocity. You can see that the velocity appears, and if I play, you can see that nothing happens, right? I'm at time step number 11, nothing is happening. Why is that? Well, that's because your legend is not changing. So what you can do is you can just click on this button which says rescale to data range. And that's basically going to rescale everything, and you are able to see what's going on. Right now, in our case, the flow is along the x-axis, right? So let's just go to the first time step and let's see what's happening. Right, you can see that there are initially some solutions that look really bad, but then over time you're slowly starting to develop that parabolic type velocity profile. Here you have a uniform profile, that's why everything is red color. And as you move towards this side along the positive x, maybe this might be a better view. I can just stop this guy. Yeah, maybe this might be a better view, so that on the left hand side you have uniform profile, and on the right hand side you have a parabolic profile, right? So this is really nice, correct? You can actually see that you're able to see very physical results from a very simple simulation. So what else can you do here? Do you remember initially I said that the incoming fluid is air, which is 77% nitrogen, but then I initialized it with kind of the opposite concentration. So if I color this by nitrogen, notice that initially I have only 0.23, 23% of nitrogen in the initial conditions, right? So you can see that the min is also 0.23 and the max is also 0.23. So if I play this guy, you can see that the inlet nitrogen is coming in. It's just washing it out completely. It's washing the initial conditions. After that, you just have your regular air, which is 77% nitrogen. And if I rescale this, you can see that immediately this rescales to 77. So let's just go back all the way to time step 0 and play this. This time, you are not able to see it as differently because the scale is too huge. And you can see that the minimum is also set to 0.77, right? So what you can do is you can go for a custom range and say that the minimum is 0 and type in rescale. And this time, go back and hit play. You will be able to see exactly what I'm talking about. So the whole reason why we are setting up a different initial condition is to show that initial condition in a continuous flow simulation doesn't matter. No matter what initial conditions you put, unless it's like super incorrect, the simulation is still going to take that data, it's going to just push it out. And eventually you will get the right results. And one thing that you need to do with a steady state simulation is you need to run it till a point where convergence is reached. So in other words, if I just stop this simulation and play it at 30, or maybe even at 10, I guess, right? So 10 here stands for 1000 cycles, correct? Because every 100 cycle you are writing an output file. So 10 means that's cycle number 1000. If you are running your simulation only up to 1000, that's not right, because your initial conditions are still not being washed away. Whereas if I just march through the time, it takes you at least 15 steps, which is basically 1500 cycles for the output to wash. Alright, this is what people call as 3D post-processing. But you don't have to do this directly. The first thing that you need to do is you need to open up CONVERGE Studio, go to the line plotting module, right? And then click on open, and you navigate to the location where you have saved the output files. Right now, this time you are not going inside output, we are actually one level above it, right? And why is that? Well, that is because the line plotting module is going to read the ASCII files, the .out files, whereas ParaView is going to read the binary files. There's a huge difference. Hope that makes sense. So let's load this guy, and immediately you can see a list of files. So the file that we are going to be looking at is area averaged flow.out. So this is basically your flow rate in the inflow boundary condition. Notice how it initially changes, but then it has reached a steady value. Similarly, what you can do is look at the mass flow rate at the outflow boundary, and that has also converged. You can look at other quantities. For example, if you type in cell count rank.out, you can look at the number of cells. In this particular case, we don't have a lot of cells, right? We have about 1111 cells, and there are 4 processors, right? If you look at rank 0, that is processor number 1, which has 277 cells, and you can use control and select multiple guys to kind of look at what's the cell count. You can see that the lowest processor number 4 has about 268 cells, whereas the processor number 2 has about 284 cells. It's not hugely different, right? So this is your line plotting module. We will be using line plotting module to make sure that we analyze different plots. So what is the last option? Well, that is your post-processing. So here what we are going to do is we are going to basically edit. We're going to go to settings, and the path to post convert is already set up here. If not, make sure that you assign the right path, and we're going to click on OK. And here, case name, I'm just going to type in test, and let's navigate to this particular folder, E:, and we're going to converge runs, and then we're going to go to support cases, channel test 2, output, select folder, and immediately you can see that the list of files is showing up. In other words, instead of using the command line interface, you can use CONVERGE Studio to convert post files into a form that ParaView can read. Remember, the file type is set to NSIDE, and that you don't want that. Let's basically use ParaView BTK binary form, and you can select everything, select all variables, and you can convert it. And to kind of show you that this process works, let me go to Sigwin, type in ls, you can see that the test files are already there. Now what I'm about to do is fairly risky. I'm going to delete all the files that were generated by the post-convert process that I ran previously. Now remember, the last time I ran it, it asked me for a name and I provided test. In other words, every file is going to begin with the text test. And I can use the Linux tool RM, which stands for remove. And I'm going to remove anything that starts with test. So it doesn't matter what the file is. If it starts with test and star basically says it can be followed by anything else, that file is going to be removed. So what I can do is, to show you this, I can have the output file to the side and I can kind of show you that, you have all these test files, but if I hit rm test star, you'll see that slowly those files got removed, right? Now what we have left is just the post files, right? I think the files are still getting removed a little bit. Okay, looks like it's done. So now if I scroll up, you can see that there are only post files. So now let's go to Converge, and here I've selected everything and I can just hit convert, and the same output that you saw on your terminal screen is appearing here. So this is a very nice option if you feel like the terminal usage is a bit hard, and especially Cygwin did not work very well. So this might be the only option that we are going to be using for now. Okay. Alright, so with that, I think I've covered everything that I wanted to in this particular series where we are running the channel flow simulation. We have basically used all the softwares that we wanted to use to basically run this simulation. So make sure that you follow this completely and just follow along whatever I did. And if you have any questions regarding the process that I followed, do get in touch with us. With that, I would like to conclude this video and I'll see you in the next one. Bye.